Hi, welcome back to our subchapter 1.1, that is pressure. So it is the force due to the static pressure P, symbol as P, in the direction of the flow is equal to the pressure multiplied by the cross-sectional area of the annulus. So therefore, the P, the pressure, is equal to the F over the area. Force over the area. And then when we rearrange of this formula, we get the force equal to pressure times with area. So when we convert this equation, and we get, as we know that the area of the circular is pi r square. And then when we have the 2 pi r here, due to the cylinder, right? So 2 pi r times pi r square, so we get the pressure P times 2 times pi r times the delta r. Alright, so that is the equation 1. And then similarly, force due to the opposite direction. So here we have another pressure plus opposite direction, right? And then we have 2 pi r times with the delta r. So when we simplify this equation, we get equation 2. And how about shear force? Shear force is the force that acting along the inner surface of the annulus. So therefore, shear force is symbol as tau. So it is times with the area. So what is the area? So this is the formula of the area. Alright, 2 pi r times the x, the distance of the boundary, the length of the boundary of the pipe, inner surface. Alright, times equal to the tau times with the 2 pi r times delta x. So it gives equation 3. And similarly, the shear force acting on the outer surface in the opposite direction can be measured by shear stress plus the tau, the difference of tau times with the area. So again, we simplify this equation and we get the equation 4. Alright, so another force that acting on the molecule is the weight. So weight is element equal to the mass equal to the density times the volume times the gravity. So it is the rho g, the density is the rho, and then the volume is the V, and then gravity is the G. Alright, so therefore when we have the volume of cylinder here, so this is the formula of the volume of the cylinder times with the rho density times with the G is gravity, so we will get this equation. However, when we have the theta here is the tilting angle of the pipe. So therefore, when we put the theta, we consider the angle, and then we can get the W sine theta, and we have equation 5. And by applying the momentum equation, so it is the sum of the force in the direction of flow must equal to 0, since there is no acceleration of steady flow. So we consider that all the force is equal to 0. And then we just, from equation 1, we minus with equation 2, right? And then this is due to the pressure. And okay, so minus with the opposite pressure, right? Plus with the shear stress of the pressure, and then minus with the opposite direction of the shear stress pressure plus with the weight of the molecule, so we can equal to 0. So that is the momentum equation. So by substituting the W, the weight, into this equation, and we can get, okay, so we integrate, we differentiate all this data, and at last we get the piezometric pressure. So the piezometric pressure is equal to P plus rho Gz. Right, so it is independent of the R. Thus, expression can be integrated with respect to R. By integrating the equation, so we integrate this equation, okay, so we can equal to 0, and by substituting the values at the center line where the R is 0, the center line, the radius is 0, therefore the C is 0. And now we go to the shear stress plus the velocity gradient relationship. So here we have the shear stress equal to the negative mu, okay, viscosity, times with the delta U over dy. So when the circular pipe distance are measured from the center R, this will modify the equation into equation 6. Alright, by substituting the equation 6, so we get the R squared over 2 times with the differentiate of d over dx, okay, pressure times rho Gz plus the radius times the shear stress equal to 0. So it will result in this equation. So therefore, we have the velocity gradient. Okay, so it will become this equation, and by the velocity obtained by integrating the expression with this, so d is the constant of integration. Alright, so we can get the velocity. And now we apply the boundary condition at the pipe wall. So where the R is equal to capital letter R, because it is the boundary condition. So the velocity at the boundary is 0. So due to the no slip condition, so it will become this equation because the U is 0. Alright. So the velocity can be calculated by using this equation. So R is the radius of the pipe, and then small letter r is the distance of the point measured, okay, and then mu is the viscosity of the molecules, and then d over dx, right, times with the pressure P, and then rho is the density of the fluid, gravity, gravitational force, and z is the elevation of the pipe. So we can get the velocity of the molecules. So we will go to the maximum velocity in the next video. Thank you.